Okay, in this section, we're going to be taking a look at quadratic functions. As you may remember from Chapter 2, a quadratic function is a function where the highest degree is second degree. Therefore, the coefficient a of the quadratic term cannot be 0, otherwise that would wipe out the second degree term and you would no longer have a quadratic function. However, the linear term, first degree term, as well as the constant may or may not be missing. The only thing that must be there to have a parabolic shape is the second degree term. You're seeing a picture of a parabola that opens upward, and in that case we are looking for an a value that is greater than 0. In other words, positive. This is how we say something is positive. And when the a value is negative, then the parabola opens downward. So that's one of the very first things you're going to check out is that a value to determine whether or not the parabola opens upward or downward. You will be expected to graph these parabolas by hand and demonstrate all the algebra that went into preparing the graph. Okay, as we go a little bit further here, notice that there is a line that comes right through what's called the vertex. This is the vertex. That's right, printed for you right there. And that axis of symmetry will always go right through the vertex, and you will be asked to give the equation of the vertex, which I will point out to you and go over with you in some of the examples that I have prepared. But basically, the equation for this line, for all vertical lines, the equation is x is equal to, you're going to discover that as we start finding the vertex, that this vertex will be called h and k, where the h really just represents the x coordinate and the k represents the y coordinate. We just give the x and the y coordinate that special name hk at the tree. The equation, the formula for this equation is x is equal to whatever that h value is. Okay, and that's regardless of whether it opens up or down. This axis of symmetry will always be named by the equation x is equal to h. And the vertex will always be h and k. Okay, there is the vertex can have the name minimum. If it is the lowest point on the entire graph, it is called the minimum point. And if it is the highest point on the graph, it is called the maximum point. So now we're going to get into all of this as we try to create our own graphs by hand, not by calculator. You can do some of the arithmetic in your calculator, but if all you can do is produce a graph by calculator, you're going to find yourself on a test, just fair warning, missing most of the points that are available for that problem. You're going to see that in these problems, as we go in graphs, sometimes the parabola will not be at the origin. The vertex at the origin means that it is a parent graph. In other words, that vertex has not shifted to the left, nor to the right, nor has it shifted up or down. But when it does move horizontally, that will be impacted based on the h value. If it moves up or down, that will be because of the k value. And we're going to talk about those things as well. Okay, and likewise, you see these are called transformations, when the vertex moves away from the origin and moves either to the right or to the left, and additionally, it can move up or down. The same thing is happening in this graph, only this is a graph that goes upside down. So it's just a picture of what some of the transformations look like. Now I'm going to show you how to graph these parabolas, whether their vertex is at the origin or whether it has a translation. You'll be able to graph all of those. Okay, I do want to talk to you about the different forms that these problems can come in. The easiest form is what we call standard form. Standard form will always have an expression that is squared, so you'll have one parenthesis, and inside that parenthesis there will be an expression x minus some h value, and you're going to be able to get part of the vertex just by observing the number here. And there will be a square. There will be no more than one parenthesis. The coefficient out in front of the parenthesis will tell you, just as we discussed on the previous page, whether the parabola opens up or down. If it's positive, it opens up, and if it's negative, it opens down. This will help you get part of the vertex, the H value, and the K will help you get the other part of the vertex. Okay, one word of warning. When you are looking for the vertex, being that it's in standard form, this is actually can also be called vertex revealing form, because without you doing any calculations, you're going to be seeing what the vertex is. Whereas when you don't have this parenthesis, you're going to have to do quite a few steps to get the actual vertex. Okay, one word of warning is this minus sign, and what does that mean? When you're looking at a formula that has a minus sign and you're being asked to identify the value that comes after it, you're going to have to remember to switch the sign, because you're going to be given the problem in standard form. And by the time they have given you this equation in standard form, the H value has already switched because of this negative sign. So you have to switch the sign if you're going to take it out there. If someone asks you, name the vertex, you have to realize that you're seeing the opposite because of this negative, and you have to switch it when you report it. However, the K value has a plus sign in front of it, which means you will use it as is. The way you're seeing it here is what it is actually equal to. So switch your H value, do not switch your K value. Okay, switch that sign on the H value. Do not switch the K value. Okay, don't switch that sign. So let's start, and I'm going to demonstrate for you when given the equation in standard form, just like you see it up here. How do you tell what the vertex is and whether it opens up and down? How do you find the into your calculator and just getting it on, just eyeballing the graph and getting it that way? You're in an algebra course. You need to demonstrate everything algebraically. Y-intercept, same thing. You're going to demonstrate that algebraically. Then you're going to take all this information, put it on a graph, and identify and the domain and the range. Those are the main concepts in the entire section. Okay, so let's start. Okay, first thing I want you to notice is that the value out in front is negative. And whenever that A value is negative, again, this is how we say that something's negative, that means that the parabola opens downward. Okay, find the vertex. Well, this is vertex revealing form, which means you are saved from doing the work of finding the vertex. All you have to do is know how to take the numbers out of the equation properly. You are to switch the sign on the H value. So it's really positive 1, even though it appears that you're looking at a negative 1. This is the K value. You do not switch that one. Use it as is, and that is where your parabola starts, at 1/8. Finding the X-Intercepts. You know that whenever you're finding an X-Intercept, you're going to find any kind of an X-Intercept. The Y value, that's what this means, will always be 0. So let Y be 0 and then find the X-Intercept. Okay, this will be the hardest part of the problem for you, because when you do this part of the problem, you need to be on top of, how do I solve a second degree equation? That was something that we went over pretty heavily. We reviewed it actually in chapter 1. There are 4 or 5 different methods for solving a second degree equation. The ones that are used most heavily and will continue to be used heavily in all your algebra courses from here on out is factoring, using the square root method, or using the quadratic formula. Those 3 methods are the ones we're going to concentrate, although there are other methods. Okay, so the most work will be for, see such a large amount of space here for us to work it out. So let's go ahead and do that. We're going to take y and set it equal to 0. Okay, what is y in this problem? Well, here's your equation. F of x is the same thing as y. This actually stands for y. So you're going to replace this entire thing, which stands for y, with a 0. So you now have a 0 on the left. Copy the right side of the equation as negative 2 x minus 1 squared plus 8. Now, whenever you have an expression squared like this, oftentimes you can use the square root method, specifically if your first degree term is missing. You don't see like a 5x or a 6x or something to the first degree. The only thing you have is a squared expression and a constant. Squared expression and a constant, and that is when the square root method is to be used to solve the equation. And you need to demonstrate that after coming through MAT 1033 and reviewing all the concepts from MAT 1033 in Chapter 1 that you now know how to solve an equation, a second degree equation. Okay, when you're solving this, if you're going to use the square root method, you cannot take the square root to get rid of the square until you isolate this squared term. In other words, you need to move this 8 over here. That'll be negative 8. At that point, you'll have negative 8 on the left side while having just a negative 2 times x minus 1 squared on the right side. This squared term is still not isolated. It has a multiplier in front of it. You want to get rid of that as well. Okay, at this point, this is gone. You have a positive 4 on the left side of the equation. I'm going to continue the problem right here. 4 is equal to x minus 1 squared. And now you can take the square root. You're going to take the square root of the squared expression as well as the square root of the numeric side. When you take the square root of the numeric side, no variables here, don't forget to report the positive and the negative root. Because for any second degree equation, you should be getting two solutions. X-intercepts are the same things as solutions. And if you have forgotten what an X-intercept is, it's where the graph hits the x-axis, but those are also considered solutions. Okay, so square root of 4 plus or minus 2 minus 1. Now to continue with this, you need to set up two mini equations. X minus 1 equal to positive 2 and x minus 1 equal to negative 2, which I will continue up here. X minus 1 equal to that positive 2, and then your other little equation will be x minus 1 equal to negative 2. And in solving these, you're going to be getting the two x-intercepts. So one of them is 3, and the other one is negative 1. And those are some things that we're going to use to create our graph. Okay, in step 4, you're going to be finding the y-intercept. When you find an x-intercept, you let the y be 0. Whichever intercept you're finding, if it's called the x-intercept, you let the other coordinate be 0. If you're looking for the y-intercept, then you let the x be 0. And that's exactly what we're going to do here. Now this is a much easier part of the problem as opposed to step 3. Step 3, you have to have equation solving ability, specifically knowing, hey, what should I use? Square root method? Should I factor? Should I use the quadratic formula? Those are all up for grabs, and depending on what form the equation comes in, that's how you make the decision of which solving method to use. So we're going to talk about making that decision and what to look for as we go through successive problems. Okay, let's continue with this, finding the y-intercept. So you're going to let the x be 0 in this equation. So let's copy this equation. Remember, f of x stands for y, so I'll just write that as y. And wherever I see an x, remember, I'm going to let it be equal to 0. Okay, so this is usually pretty simple. You have a negative 2 out here. You have a negative 1 in the parentheses plus 8. So -1 squared is 1, positive. When you square, you always get a positive. And then possibly by something that'll turn it back negative. But this part is positive. So +1 times -2 is -2 plus 2, 6. So your y-intercept is 6, which you can leave like that if you want to. You can just go to the y-axis and plot a point on 6, or you can actually write it as a point if you'd like. And you want to pay attention in MyMathLab 2 or whatever software you're using to which form they want you to give the answer in. We got this answer for y, 6, by using 0 as the x-coordinate. So either way. But these can be written like that also. You can write this as x is 3, y is x3, because we allowed y to be 0. You can sometimes have 2 x-intercepts you're going to see in this problem. Sometimes you're going to have 1 x-intercept because the graph only touches the x-axis at that one point. Sometimes it actually cuts through at 2 different points. So this can be written like this. And sometimes you have no x-intercepts at all. That'll be when the parabola is above the x-axis and opening up. Or sometimes it can be below the x-axis, opening down, and therefore it makes no contact with the x-axis. You'll see all of that as I do these problems. Okay, so we now have the x-intercepts. We now have the y-intercept. We know the vertex. We know which way it opens. And by putting all of this together, this is what the main emphasis of college algebra is graph theory. So I know I sound like a broken record. If your only ability in this class is to stick an equation in your graphing calculator and let the calculator do it for you, then you will not be passing the test. So make sure that you know how to do it by hand. Students are very tempted to be calculator needy. Okay, so graph the parabola. Let's put everything we have. We're going to put the vertex. I think you should always label the vertex so that you know you're opening from there. Okay, so we're going to go to 1 and we're going to go to 8. 1, 2, 3, 4, 5, 6, 7, 8. So right here. Remember that we had decided at the beginning of the problem that we're opening down. So this is my vertex at 1, 8. And the way we're going to develop the rest of the graph is information that we found. We found out that the x-intercepts were at 3. An x-intercept is a point on the x-axis, and there was another x-intercept at -1. We also found through our algebraic calculations that the y-intercept is at 0, 6. So that's going to be right here. Y-intercept is a point on the y-axis. So as we start to connect, remembering that we're opening down from the vertex, you're going to pass through this y-intercept, pass through the x-intercept. You're passing through anything you know is a point. And then on this side, we don't have as many points, but we still have enough. So this is the other side of the graph. You're also going to be asked to give the axis of symmetry in most of these problems. That is a line that comes from the vertex vertically. So this is your axis of symmetry. I am going to name it. There's a formula for the axis of symmetry, a formula for the equation of this line, and it is x is equal to h. So the name of this equation is x is equal to whatever the h value is. Remember, I know you see this as an x and a y, but at the vertex we give it the special name h and k. So that h value is 1, and therefore my axis of symmetry, which I'll just abbreviate like this, there's the equation right there. Okay, so we have our graph, we've done all the algebra, we have the axis of symmetry. You're also going to be expected that for a parabola that you know how to state the domain and the range, and that will appear in most of the problems as well. That comes from looking at the graph. First of all, you need to remember domain is all about what are the x's that the graph is demonstrating. And you need to know what range is. Range is what are the y values that the graph is demonstrating. One thing that can be deceiving about these graphs is that some students think that the legs go straight down. but actually what they do is they flare out. So think of this leg, and that would be if you continued to graph more and more and more points on the sides of the parabola, you would see these legs flaring out continually to the right, which means this leg goes out to x values that are considered, infinite, positive infinity, and this leg flares infinitely to the left. So when you're talking about domain, you are talking about the width of the graph. How far does it expand horizontally? This leg goes horizontally all the way out to positive infinity, and this leg flares out to negative infinity. So it is said, they want us to use interval notation, that the domain x values go from negative infinity to positive infinity. Don't forget, with interval notation, we have used it often when solving an inequality, but we also use it when we are talking about domain and range. You must state the smaller quantity first. Okay, now moving to the range. Look at the range. The range is about how high and how low does the graph go. In other words, you want to talk about all the y values that you're witnessing on the graph. So notice that the very maximum, because remember we were talking about the vertex can be called a min or a max. This happens to be called a max, a maximum. And that's because it is the highest point on the graph. So if this is the highest point on the graph, then this is the maximum y value, and that's the maximum x value. So when they say, what is the maximum y value, which you can use when you're talking about the range, that would be the 8 that you're seeing there. Leave that off. I can put it down here. So the very highest y value is 8, and then the y values on the legs get smaller and smaller and smaller. So we say when something's getting smaller and smaller and smaller, it is said to be going into negative infinity. When it's getting bigger and bigger and bigger, it's going to positive infinity. Okay, so we're going to be naming the y values like this. The y values are anywhere from negative infinity down here all the way up to the very most biggest y value or maximum value called 8. And since the graph actually goes through that point, we have a bracket around the 8. All infinity symbols carry a parenthesis to enclose it. Okay, so that's your first problem by hand, and what we concentrated on in this problem was an equation or function of the form a times x minus 8 squared plus k, which is referred to as standard form. It'll have one parenthesis in it with a square. Okay, moving to this next problem, example 2. Note that you have, again, a second degree standard form function, quadratic function. I picked this problem because sometimes students get tangled up with the order in which the terms are listed, and sometimes don't realize which one's the a value and which one's the b value. So you might want to rewrite that if you do have that issue. Some students like to write the squared term first, because always in front of the squared term is the a value. So that minus you're seeing, that's a -1. That's a -1. The 9 is positive. So this problem can be, you can rearrange the terms like this so that you're not messing up with the a value. That's your a value. It does happen to be negative. And therefore, this parabola opens downward again. There is no b value, and that's because whenever you're being given something in standard form, you're only going to see an a value. It'll be a coefficient of the squared term, and you're going to see a constant. That constant's always considered the k value, actually. So now moving on with this problem, we have the vertex that we're looking for. Remember the vertex, when it's in standard form like this, that you need to pull the h value out of there. and switch the sign. But don't switch the sign on the k value. Okay, so you have the vertex. Finding the x-intercepts is going to require knowing what solving technique to use. When it's in standard form like this, you're going to be using the square root method to solve it. Whereas when we move to other forms that the quadratic equation can possibly be given in, we will no longer be using the square root method to solve it. So I'll make sure that you are exposed to all the solving techniques as we go through this lecture. Okay, so finding the x-intercepts, just replace the y with a 0. Let it be equal to 0. This is the y right here. So we let that be 0 while copying the other side of the equation. And you can copy it as it was given, or you can copy it this. It really doesn't matter. You're still going to have to go through the same number of steps. Remember, when you are trying to solve second degree, through the square root method, you need to isolate the squared terms. That means you need to bring the constant to the other side. In this case, it would make it a -9 because it's moving over here and switching signs. So at that point, you have a -9 on the left and a -1 times x minus 2 squared on the right. You want to get rid of the coefficient that's being multiplied by that. So we can divide that right off there by dividing by -1. Likewise on the left-hand side. Okay, -9 divided by -1. Finish that up here is +9. And what we have on the right-hand side, this negative gets rid of this, is just x minus 2 squared. Okay, now you're ready for taking the square root of both sides, which is why it's called the square root method. So take the square root of the squared expression, take the square root of the numeric expression, and don't forget to report both the positive and negative root for the number. Okay, so square root of 9 is 3, so it's plus or minus 3 is equal to x minus 2, because at this point the square root dissolves the square, out comes the x minus 2. Okay. Now you're going to create your two mini equations by setting x minus 2 equal to +3. And also setting x minus 2 equal to -3. When you move this -2 over here, it becomes a +2, leaving you with x equal to 5 as one of your x-intercepts. When you move the 2 over here, that also becomes +2. -3 plus 2 is -1. So that's your other x-intercept. So we have both of our x-intercepts. Again, you can write them like this, or you can just write them like this if you'd like. X is 5 because we allowed y to be 0. X is also -1 because we allowed y to be 0. So you can write the x-intercepts like this. Okay, find the y-intercept. When you're finding the y-intercept, you want x to be equal to 0. So we're going to go up here and grab the expression again. This says y is equal to, and then you're going to be plugging into that. So 9 minus x minus 2 squared. We're supposed to be putting in a 0 for x, so that goes right there. This is going to be 9 minus -2 squared, which is 9 minus -2 squared is 4, which is equal to 5. Okay, so we have y is equal to 5, which can also be written like this. Y is equal to 5 because we allowed x to be equal to 0. Any of these intercepts can be written as points. Okay, moving on to the graph, where we're dumping all of what we have found onto the graphing grid, naming the axis of symmetry, as well as the domain and the range. Okay, so we know that the vertex, let's put the vertex on there first, is 2, 9. So we're going to go 2 and go up to 9. Right here is 8, so we'll just go a little bit above. Call that our vertex, and I can label up here because I'm going to be opening down, so this won't be in the way. Okay, the other things that we found as far as plottable points, we found out that the x-intercepts on this graph are 5, 0 and -1, 0. We also found out that the y-intercept is 0, 5. And we can connect to get our nice full graph. Try to hit the points, unlike what I just did. Then you can go and put your axis of symmetry in. That goes right down the middle, splitting the graph into 2 mirror images. Okay, this half is completely identical to this half. And anything that has, if this leg has a point right here, then on the other side of this axis of symmetry, spaced evenly apart, notice that this point that's on the left leg is 2 spaces away from symmetry, then that means there's another point over here, 2 spaces away from the axis of symmetry. They'll have the same height when they are mirror images, and they'll be evenly spaced from the axis of symmetry. In fact, when you fold the paper right on this line and you open it up, you have 2 identical images. So anyway, back to the equation of this axis of symmetry. Formula is, let me keep reminding you of it, x is equal to the h value. The h value is the front value, and this value back here is called the k value. So this will be x is equal to 2, and that makes sense because every point on this line has an x value of 2. The entire line has points that have x value of 2. Okay, then after we get the axis of symmetry, we're going to talk about the domain and the range by looking at the graph. Again, all parabolas will have the 2 legs that expand infinitely to the right, and this is all vertical parabolas. I should be more specific because there are parabolas that go sideways. They're not functions, but they do exist. So let me be clear. When you have a vertical parabola, either a parabola that opens up or down, both legs flare out. If you were to continue plotting, we just have so much room on this paper though, so we're not able to see that it flares continuously. This goes out to the right continuously, and this goes out to the left continuously. So since how wide a graph is what we refer to as the domain, because it has to do with the x values. The x values on this graph would be anything from -infinity to +infinity because of how the width expands. So in interval notation, here's your domain. Domain will always be this for any kind of vertical parabola. When you're looking at the range, then you need to consider the vertex as well as which way it opens. Okay, this opens down. That means that the y values go all the way down to -infinity. If you allowed this graph to go on and on and on, the y values would eventually go to -infinity. In other words, getting smaller and smaller. However, the maximum y value is what you're seeing right here at the vertex. That maximum y value is this 9 right here. So we're going to say that the y values can be anything from -infinity down here all the way up to 9. -infinity all the way to +9. Okay, and that's a discussion of the y values on the graph. Okay, moving to example 3. In example 3, one more standard form problem. I wanted to do this one because each one has its own little issues that tend to trip students up. With this one, I think what disturbs students sometimes is the fact that they're looking for the x-intercepts and they don't really know what went wrong in the problem, but let's talk about that. So first of all, does the parabola open up? Notice that the a value right here is +1. That a value will always be found in front of the squared term. So because the A value is positive, we're going to open upward. Find the vertex. The vertex, because it's in standard form, it automatically reveals the vertex for you without you doing the work. You just have to remember to switch this H value right here to positive 3 because you're already seeing it in switch form. So in actuality, the H value was really positive 3. And then the K you do not switch, so that's your vertex. Finding the X-Intercepts, you're going to let Y be equal to 0 in this equation. So let this be equal to 0. You're going to get x minus 3 squared plus 1. You're going to use the square root method to solve it. Okay, don't forget you have to isolate the squared term. That means bringing this over here, at which point it becomes a negative 1. So now you're looking at this. You have a negative 1 on the left. You have a squared expression on the right. Now, right now, you might sense that there is a problem because some students will be able to analyze this in the form that it's now without doing any further algebraic maneuvers. First of all, if you're taking some expression and you're squaring it, isn't it true that when you square any kind of a number, because x stands for a number, so no matter what you square, if they're integers, and we're using integers to plug in for x, you can never get a negative. So this is impossible for this to be true. And whenever it's impossible for an equation to be true, we say that there are no solutions for that equation. And why were we solving this equation? To find the X-intercepts. So if there's no solutions to this equation, there are no X-intercepts. Some of you are not going to think on that level. You may just continue with your algebra and go like this. And this should also tell you, hey, there's a problem. You might say, okay, now I'm ready to get rid of the square, and I'm going to take the square over here, root over here too. I need to report the positive and negative root, but what do you have at that point? You have plus or minus I. The square root of negative 1 is I. And then here you are into some imaginary numbers. Eventually, even if you were to continue and bring 3 over here, you would have positive 3 plus or minus I. And you can write the I first or 3. But in any event, this is like saying that your X-intercepts are part imaginary. You don't have any imaginary numbers on your graphing grid. You are graphing within the Cartesian plane, and all there are integers there along the x-axis as well as the y-axis. So by saying this is the same thing as saying there are no x-intercepts because these kind of numbers are not possible within the plane that you are graphing. Okay, so what this means graphically is that when you go to graph, your whole parabola is either going to be above or below the x-axis, so it won't have a chance to touch the x-axis, which is what no x-intercepts mean. Now, since you are opening upward, that means your whole parabola is going to be above the x-axis, opening upward, never giving it a chance to touch the x-axis. Okay, find the y-intercept. When you find the y-intercept, you let the other coordinate be 0, x. So we're going to copy the equation that we started with. Y is equal to x minus 3 squared plus 1. Y is equal to x minus 3 squared plus 1. And we're going to put a 0 in here for x. This will give you negative 3 squared plus any number squared, any integer squared is positive. So that'll be positive 9 plus 1 equal to 10. Okay, so now my y-intercept is 10. And again, you can write these as points if you want. When letting x be 0, we got an answer of 10 for y. Okay. Now taking everything that we have calculated algebraically and putting it on the graphing grid, we knew that the graph opened at 3, 1. 1, 2, 3, 1. That's our vertex. We also know that it's going to open upward, so I think I can safely label the vertex right here. That'll be out of the way because we're going to be opening upward from here rather than down. Okay, now going to put anything else that I know. I don't have any X-intercepts. I do have a Y-intercept of 10. And let's see, this goes up to about, by the time you get here, that's about 9. So we'll just add on to this graph. 9, this will represent 10. Okay, so 0, 10, that's going to be my Y-intercept, even though my Y-axis didn't quite go that far, but we can always fix that. So we don't really have much on this particular graph. All we have is a vertex, and we have this one point that we can go through on the Y-axis. However, how do we get the other side when we don't have as much information as we've had in the previous problems where we had X-intercepts to go through and Y-intercepts to go through, and that gave us a nice full graph. Here's where you need to start thinking about your axis of symmetry and how there are mirror image points on either side of the graph, because this will stop you from having to do further calculations if you understand how the axis of symmetry functions. Why don't we draw that? Axis of symmetry always goes right through the vertex, and straight up is equal to h, with our h value being 3. So that is, we did this part already. Okay, now using this axis, we don't have many points, and understanding that any point that you see over here, like for instance, you had a point over here for sure. I mean, you don't know the values of any of these other points, although we could figure them out. But let's just use what we have already. If you know that you have a point called 0, 10, and you analyze where is that point with respect to the vertex, like how far would I have to move to the left and how far up would I have to move to get right on that point if I was standing on the vertex? How do you travel from the vertex to this point, making horizontal and vertical moves? Well, if you're over here at 3, to get right up underneath that point, since it is on the y-axis, an extension of the y-axis, I would have to move 3 to the left, and from where I'm at 1 already. I'm up at a height of 1. I would have to move 9 spaces up. If I'm already at 1, I'd have to move 9 spaces up to get to 10. So mimic those moves, and you will have another point, actually the mirror image of this point, on the other side of the axis of symmetry. Okay, so again, I move 3 to the left, 9 spaces up. Instead of moving to the left, move to the right. Just go 1, 2, 3, and then 9 spaces up, and you'll be, let me get these out of the way. Shouldn't have labeled that there because I need to plot a point. So 3 spaces, 1, 2, 3, and move 9 spaces up, and you're right at that height of 10. Right there. And this is the mirror image to this point called the Y-intercept. But it also gives you a perfect symmetrical width on that parabola. It gives you the other side of the parabola. And I can put this right back here as my axis of symmetry. And so you have everything there. Then discussing the domain and the range. Okay, again, domain is x's. All parabolas flare infinitely towards positive infinity. And this leg over here on the left flares out this way to negative infinity. So the domain is negative infinity to positive infinity. Then the range is what the y values are demonstrating on this graph. The y values, okay, remember that you need to look at the vertex and which way it opens up. So this is called the minimum value. And therefore the minimum y value is right there. So this is the very most minimum y value on this graph, the smallest y value. And then as you travel either on the right leg or the left leg, those y values are going up, 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 all the way to positive infinity. So the range is said to be, remember we have to name the smallest y value first. We're only talking about the y's in this interval. Those y values go from 1 at its smallest all the way to positive infinity. And there you have all parts of that problem. Okay, now moving to a different kind, a different form of a quadratic function. What we have seen in examples 1 through 3 has been a quadratic equation in standard form where it had one parenthesis with a square on that parenthesis, and we were very easily able to get the vertex without doing any work, at least for that part of the problem. However, now you're in what's called general form, and this form does not reveal the vertex. You're going to have to know formulas for getting the h and the k value, where in examples 1 through 3 we were just able to snatch it right out of the equation. So when it's in this form, you have to be real clear about what the a, the b, and the c value is, things that you had to know when you learned how to use this quadratic formula. Again, in front of the squared term is always the a value. It is -1 in this case. In front of the first degree term, the linear term, that will be your b value. And then the constant is considered your c value. Okay, so now when you excuse me, when you go to determine this, does the parabola open up and down? It's still all about the a value. That a value was negative, and therefore this parabola opens down. As far as the vertex goes, as far as I was telling you before, that you need a formula for this, so you're going to still be looking for h and k. To find h, the formula is b over 2a. The h is always the front part, the x-coordinate of the vertex. So -b over 2a Okay, so the b value here is -2, and then the a value was -1, so we have +2 at the top, we have -2 at the bottom, that turns out to be -1. So we have -1 as the front part of our vertex, and then the k you find by substitution. Now remember, when you are looking at these, when you're doing these values, the h value that's in the front, notice it's up in the front of this point. Anything that's up in the front is synonymous. The first coordinate is synonymous to an x coordinate. Therefore, you're allowed to use this value anywhere you see x. What we are looking for now is the k value. And notice that the k value is in the back, which is synonymous to the y value. So when you find the k, you're really finding the y value. Okay, so being the case that these both mean the same thing, we're going to actually use the equation for y. So y is equal to -x squared minus 2x minus 1. And what you want to use for the x value is this h that you just found, because it is equivalent to the x value. So we're going to take the -1 and put it everywhere there's an x. So bottom line, you will find the h value by formula, and you will find the k value, or in other words, the y value, by substitution. You're just going to take this h value that you just found, substitute it into the right-hand side of the equation, understanding that when you substitute in there, you're finding the y value. So let's continue to do that. This is -1 squared, that's 1, just for this part. But then the extra negative that you see out there turns it back negative, so that's -1. -2 times -1 is +2, and then another extra -1. So altogether, -2 plus 2 is 0. Okay, so there's your complete vertex. But you see that's a lot more work than when it's in standard form, as examples 1 through 3 were. Finding the x-intercepts, back to your ability to solve an equation. Only now we won't be using the square root method. You are to use the square root method when the equation, the quadratic function, is given case, like I said, examples 1 through 3. Okay, find the x-intercepts here. Remember, you always let y be 0 when you're looking for an x-intercept. So come into this equation, f of x stands for y, let that be 0, and copy the right-hand side, which is -x squared minus 2x. So now you see that you now have an equation that's not in standard form. It doesn't have a parenthesis with a square on it, so you can't use the square root method. You can actually see the a value, the b value, the c value, therefore you should be factoring. If you attempt to factor and you cannot get integer values, then go to the quadratic formula to solve it. But the square root method is not something that you would use here. Okay, one thing you might want to do, unless you're into negatives, is get rid of these negatives. It'll make the factoring easier. Divide this entire side by -1, which forces you to do the same thing on the other side. 0 divided by -1 is 0, and the effect of dividing by -1, it'll change the sign on each of these numbers. So negative divided by negative, that turns into positive x squared. The -2x turns into positive 2x. And -1 divided by -1, that -1 turns into positive 1. So division by -1 changed each of these signs. Now you can go in with your slightly easier to look at equation and get it factored. Okay, you have 3 terms here, and you can, a very easy way to graph this one, especially when the numbers are so simple like this and small, is just to ask yourself, what factors can I break this up into? And that will fill in the front position of each of these parentheses. So the only way you can factor this down is x times x. So these two factors, when multiplied together, give you x squared. To fill in the back position, it's what factors, how do you factor down the constant? The only way you can break down a 1 is 1 times 1. As far as the signs go, when the last term is positive, both of these are the same sign, and this is what they both are. They're both positive. Now, I would tell you to create 2 separate equations as we did in examples 1 through 3, but you're just going to be getting the same answer twice, so therefore there's no need to do that twice. Just take one of those factors, x plus 1, set it equal to 0. You're using the 0 factor property when you do that. Things multiplied together are 0. Then either this one has to be 0 or this one has to be 0 or both. And that's what allows you to do that in each of the problems. So that turns out x is equal to -1. And that means you only have one x-intercept because you had twin factors. Finding the y-intercept, you're going to let x be equal to 0. So again, go back to this equation. This time you're putting the 0 where the x's are, and f of x just stands for the y that you're looking for, y-intercept. So this is going to be -x squared minus 2x minus 1. And we're putting a 0 in wherever there is x, which wipes out the first term, wipes out the second term, and it leaves you just with -1. So your y-intercept is -1. Again, you can write those as points if you want to. You can write this as 0, -1, and you can write this as x is -1, y is 0. Putting that information on the graph, we had a vertex at -1, 0. And then it turns out that our X-intercept is also -1, 0. So this is we're gonna end up with even less points here. Again, you're gonna have to fall back on your axis of symmetry to create mirror images unless you want to do more calculations, because you do have to show how you got these points. So we got from our work up here, we said that the vertex was at -1, 0, which I have already put on the graph. And then the x-intercept was -1, 0, so we have that already. Then we have the y-intercept, which is at 0, -1, which is down here. I would label your vertex so you know where you're opening up from, because students get confused and start opening up from other points. So this was my vertex right here, so it'll be safe to label up here. And this was -1, 0 for my vertex. So from here, I'm going to spill down like this. So I could go through this y-intercept to get one side of the graph, but how do I get the other side of the graph? So that's why, unless you want to do further calculations where you pick any x you want, as long as it's over here, you should just learn how to use axis of symmetry. Again, axis of symmetry splits right down the middle. It splits the parabola right down the middle coming from the vertex. That axis of symmetry is called x is equal to whatever the h value is. And in this case, the h value is -1. Remember, that's called h, that's called k. So there's my equation for axis of symmetry. Okay, using the axis of symmetry, now that we have it drawn in, notice that this point right here is, with respect to the vertex, it is 1 to the right, 1 down, 1 to the right, 1 down. So you're just going to move 1 to the left, 1 down. And as soon as you have any two mirror images, you've established the proper width of the parabola. So you're going to come right down through here. Now you have two legs that are equally spaced from the axis of symmetry. Okay, everything is done except the domain and the range. Domain, I think we've discussed that enough. Both legs flare infinitely to the left, infinitely to the right. So the domain is said to be -infinity to infinity. The range is all about the y values that you're seeing on the graph. Right here you're witnessing the maximum y value, which happens to be 0. That is the absolute biggest y value on this graph. Once you start moving along the legs, the y values are getting smaller, smaller, and smaller, and are said to reach -infinity. So you want to talk about -infinity, and you want to talk about the 0. What's smaller? Because you must say the smaller quantity first, or they're going to mark it wrong when you go into the homework software. Interval notation requires smaller quantity first, bigger one as the last thing you mention. Okay, moving to example 5. In example 5, we have yet another problem, but in, let's see, this would be general form. It is not in standard form as examples 1 through 3, where you had the parenthesis and the square. All you have to do is look at the a value. That a value is negative, therefore the parabola opens down. And just with that visual, without actually looking for X-intercepts and Y-intercepts and all of the things that we've gone through in all the previous problems, so without graphing, you can determine that, hey, because it opens this way, that very top, which is called the vertex, is also a maximum point, because that's the highest point on the graph. Okay, so it has a maximum value. Now it starts asking, find the minimum or the maximum value. We decided that there is a maximum value, and when they ask you for either the minimum or the maximum value, they are asking for the y-coordinate. And when they say determine where it occurs, they're asking for the x-coordinate. And both of these things that they're asking for are at the vertex. So remember, the vertex has formulas for it. You're being asked for the x and the y at the vertex because they've asked you for the maximum value. So remember that when you're looking for a vertex and you've been given the quadratic function in general form like this, that you're going to find the front part like this, and you're going to find the back part by substitution. Okay, so let's go ahead and find, now we typically call this h, but don't forget, h is synonymous to x. We typically call this k, but k is synonymous to y, so keep that in mind as we do these problems. Okay, here I go, finding the x value. That x value is found by negative b over 2a. So it's negative b. This is your b value right here, the 6. And I'll just keep saying this also. The c would be the 13, including the negative x in front of it. We've not had a chance to use the c value yet, but we will in some of the application problems. So here's my b value. Put that right in there. I have switched it. And then it's 2 times the a value. The a value is negative 3. So this is negative 6 over negative 6, giving us positive 1 as our x value. So even though the x value was asked at the end of the question, you needed to do it first so that you could get the y value. It always goes in that order. So where does it occur? Let's see. At x equal to 1 is where this maximum value occurs. Okay, what is the maximum value? Well, you find the maximum value by substitution. So it's y is equal to -3. And when the quadratic function is this form, it's super easy to do the substitution because you're just substituting in this x value that you just found, using the maximum x to get the maximum y. Move this over a little bit. Okay, and so then it's y is equal to -3 times 1. That's -3 plus 6 minus 13. So you end up getting, let's see, -3 plus 6, that's 3. +3 minus 13, and you can just put that, you can use your calculator for. You can put that in your calculator to do that, but not to do the graph theory. Okay, so we now know that this maximum y value is equal to -10. And this x occurs at 1. Okay, give the equation for the parabola's axis of symmetry. Remember that we had a formula for that, and it is x equal to the h value. Well, when you found these coordinates, the x and the y coordinate, you were finding the x and the y coordinate at the vertex. The x stands for h, so we're going to go x is equal to this front value. The x value was 1, and there is your formula for symmetry. Identify the function's domain and range. We didn't truly graph this thing, but we know enough about it. We know that it opens downward. We discovered that in part A because of the -a value. And we know the vertex. This vertex was this maximum y value that we found at an x value of 1. So at an x value of 1, we have a y partner of -10. So just from those two things, but without truly graphing the function and doing all the intercepts as we have in the previous problem, you can still find the domain and the range. Okay, domain for all of these parabolas, -infinity to infinity, and then the range, you have to really look at the graph. You got to look at the vertex and which way it opens up. So this is the maximum y value. Remember, the range is you discussing what are all the y values on the graph. That's all you're talking about with range. Domain, you're talking about x's. So the maximum y value is -10, and then the y values get smaller because all the y values that are on either the left or the right leg, they're going down. They're all underneath -10, meaning -11, -12, -13. So they're getting smaller and smaller and smaller, and they are said to go to -infinity. So the range is anywhere from -infinity up to its highest value, that maximum y value right there, of -10. Okay, so I think we have beat the heck out of finding all the things that you're going to be expected to do in showing that you know how to graph a parabola by hand, whether it is given to you in standard form with the 1 parenthesis squared, expression squared, or whether it's given to you in general form. Now we go off into some of the other types of problems that you'll be asked when you do the homework online. One of them is to write an equation in standard form of a parabola that has the same shape as 6x squared. All this gives you, when they give you that 6 tells you certain things about the parabola, as you may have picked up hopefully from this lecture. That it tells you that it opens up because it's positive, and it also determines how wide the parabola is. So that's what they mean by you want to write an equation that has the same shape. So all you need to do when you write your equation is use that same coefficient and use this vertex. You're being asked to write it in standard form. So what is the standard form equation? It goes like this. F of x is equal to a times x minus h. This is what a quadratic equation looks like in standard form and one of the formulas that you need to memorize. So there it is right there. You want it to have the same shape, then give it the same coefficient as this, and then put the h and the k. This is your h, this is your k, because they're telling you these are the coordinates at the vertex. And that's it. Don't you wish all the problems were that simple? So that's number 6. Then we get into some application problems, and in these application problems, you're going to be asked to analyze a diagram and bring in the concepts that you have learned as you graphed all of these graphs that we did in the lecture. So one thing that I should explain to you, that a lot of the application problems have to do with releasing an object, throwing an object into the air. Something that becomes airborne, it is released at a certain height. It goes and travels up in the air, as you see right here. So this is the point of release. It travels up in the air, and then, as you've heard many times, what comes up must come down. So eventually it starts coming down. And in following this path, we say that this is a parabolic path. It's the shape of a parabola. This would be your Y-intercept, this would be your X-intercept, this would be your vertex, and they can ask you questions based on those concepts that you've been practicing throughout the section. Intercept, vertex, all of these things. The hard part for students is trying to understand what is the question asking, which is what I'm going to go over with you now. Here's your function. Notice that you have a bunch of crazy decimals here. So when you go to solve this, it's going to be in your best interest to use quadratic formula. You will not be using square root method. You will not be factoring. As stated at the beginning of the lecture, you need to know all 3 methods for solving a second-degree equation. We've used factoring in a couple problems. We used the square root method. Now we will move to the third and final solving method, which is square root. I mean, not square root, excuse me, the quadratic formula. But let's wait until we get to that part of the problem. So first question is, what is the maximum height? And probably by now you're getting it in your mind that when they ask for them, they're asking for the vertex. Okay, so when they say what is the maximum height, they want the y value. That is what this word means right here. And how far from its point of release does it occur? So when they say this is where the ball is released, right here at x equal to 0. And they want to know, we're looking for this vertex right here. And they want to know how far from the point of release does that maximum value occur, that maximum height. Notice that this is the highest that this object goes. It's actually a shot put that's being released into the air. So really they just want the x value. How far from the point of release, then they're asking for the x value. So you're doing nothing more than finding h and k. Okay, so when you go to do this, let's remember that you have to find x first. X is synonymous to h. They're one and the same thing. And the formula for h is negative b over 2a. So you're going to be looking for that. Opposite of the b value, well, here's all your numbers up here. This is a, including the sign that's in front of it. This is b. This is c. So opposite of b, your b value is 0.6. You don't need that 0 right there. That's not necessary for doing our calculations. And then it's 2 times a. The a value is all of this. So negative, you can just use the 0.01. You don't need the leading 0. Okay, then go ahead and when you put that into your calculator, you're going to get 30. Okay, once you have the x value, so that goes right here, 30 feet, then you can find its y partner. So remember, the y partner is the k value. And you get that by substitution. So you want to, that stands for y, which is negative 0.01 x squared plus 0.6x plus 6.2. And the way that we always found this was we took the x value we found at the vertex and plugged it in. Okay, definitely want to use your calculator for this, and when you press all of these numbers in, you will end up getting 15.2. So the maximum height is 15.2 feet. You'll have to see if, I don't know if they want you to put that unit in there or not. Usually if they offer it to you, you obviously don't have to put it in because you'd be putting it in twice, but I don't know about this one. 15.2. Okay, so what is the shot's maximum horizontal distance to the nearest tenth of a foot or the distance of the throw? What is the shot's maximum horizontal distance? By the time you're at this vertex, it has traveled 30 feet. In fact, you know, we just found that. We said that it has traveled horizontally 30 feet by the time it gets this high in the air. That maximum height being 15.2. However, they want to know, you know, at that point, it does keep flying, flying, flying until it finally hits the ground. So at that point, when it hits the ground right here, that's the maximum horizontal distance. It had only traveled part of the horizontal distance, and it kept going until it reached its final horizontal distance. So we want to find out what that X-intercept looks like. It looks like it's almost at 70, but not quite. So we're going to do a calculation to be exact with that answer, because obviously the software you use will not accept anything other than an exact answer. So in part B, we are looking for the X-intercept. So again, all the things that you reviewed and went over in this section. So how do you find an X-intercept? Well, what we learned in every single problem that we've done thus far, or examples 1 through 5, is that you find an X-intercept by letting y be equal to 0. Okay, and you can see that on any graph, when you are finding an X-intercept, the y value of any point on the x-axis, which is an X-intercept, is y is equal to 0, which is why that's the technique. So, using the equation, if we're going to let y be equal to 0, that would be the same thing as taking this quadratic equation and putting a 0 in right here. Not in there. Okay, you put it right here. This entire thing, f of x, that symbolism stands for y. You get rid of all of that, replace it with a 0, copy the terms on the right side. Okay, now you're going to solve. But again, square root method's not going to work for you here. Factoring is not going to work for you here. So what you want to do is use the quadratic formula, and therefore you need to be aware of that formula. We use it a lot in Algebra 1 pre-algebra classes. In every math class you're going to be using quadratic formula when the problem concerns second degree. Okay, so here we go. Remember, this is A, because there's an A, B, and a C that you need to plug into the quadratic formula. So finally, you get to use the C. Here's your quadratic formula. It's x is equal to opposite of b plus or minus b squared minus 4 times a times c all over 2a. So when you go and plug in this, it's going to be opposite of b, opposite of b right here, plus or minus b squared minus 4 times a times c, 6.2. divided by 2 times the A value. And then, just to make this, somewhat doable, I think that you should probably put all of this, what's underneath the radical, in your calculator first, and then re-enter the whole thing. So when you put all of this in the calculator, this all becomes 0.7797. That's after you do this calculation and take the square root of it. So you're going to be doing negative 0.6, that's this number right here, plus or minus 0.7797 divided by 2 times 0.01, 0.02. But with a negative, because there's a negative there. Okay, so you're going to be doing 2 solutions here. One of the solutions is going to come from negative 0.6 plus 0.77. 7797 divided by all of that divided by, and I would get the answer to this first. Otherwise, you're going to have to do that. Divided by negative 0.02. And the other answer is going to be negative 0.6 but this time it's going to be negative 0.6 minus 0.7797 divided by negative 0.02. And you're going to see which of these solutions makes sense. Okay, you know that this is a positive distance, so if it's over here on the positive side of the x-axis, so if either one of these comes out negative, and you can maybe already see which one's going to come out negative, then you throw that answer out because it wouldn't make sense with respect to the actual problem. So let's see. When we put this one right in here, we go negative 0.6 plus 0.7797. Get that top first. Okay, I got that first. That way I don't have to put parentheses around it, but I put the parentheses there just in case you forget. Then divided by negative 0.02. Divided by negative 0.02. And you get one answer is, so you can throw that answer out. This thing did not travel negative 8.9 feet. It traveled a positive number of feet. So we can throw that one out because it's negative, and it must be this answer right here. So let's go and put that one in. Negative 0.6 minus 0.7797. Get that answer on the top. Divided by negative 0.02. Nearest tenth. We're rounding to the nearest tenth. So if you're rounding to the nearest tenth, let's review that. This is the tenths place right here. You're deciding whether you should keep what's in the tenths place as a 9, or should you round it up to a 10? So you look at the number next to it. It says create a 10 out of this. Well, if you're going to create a 10 out of this, there's only place for one number there. The 0 would go there, the 1 would carry here. So 69.0. Okay, from what height was the shot released? Well, let's talk about that. When you release the shot at the beginning of the problem, this is the point of release right here. At the point where it's released, x is equal to 0. In other words, the shot put has not traveled at all horizontally, so therefore the x-coordinate is 0. And when you're letting the x-coordinate be equal to 0, you are finding the y-intercept. Okay. So, at the point of release, the object has traveled 0 feet horizontally. And horizontally refers to the x-coordinate. So what I am saying verbally here is the same thing as saying x is equal to 0 algebraically. And you're looking for what is the y-intercept. Okay, so we're going to take that equation that we initially started with, which was y is equal to negative 0.01 x squared, that was the first term, and then it was plus 0.6 x plus 6.2. And if we're going to let x be 0, that means we're coming in here and we're putting a 0 right there, which is going to get rid of that term. We're putting a 0 right here, and that's going to get rid of that term, leaving us with just 6.2 for our y value. Okay, so to answer part C, 6.2 to the nearest 10. Last problem. Problem number 8. You're looking for how to maximize an area that's described is Farmer Ed has 450 meters of fencing to work with. He wants to enclose a rectangular plot that borders on a river, which means he's using the fence for only these 3 sides, not that side. If Farmer Ed does not fence the side along the river, find the length and the width of the plot that will maximize the area. What is the largest area? So again, this all relates to what we've been doing throughout the section, and let's tackle each part of it. The width, labeled X in the figure, is how many meters? And they've already labeled this for you. They're saying that both of these sides are equal. We don't know what they are, but if we call them the same variable, then that means they're going to be forced to be equal. And the way that they got this expression is if you know you're going to use up X feet of fencing here and X feet of fencing there, then in total these 2 sides add up to 2x, 1x and 2x. So you have to say, what did I start with, 450, and subtract out what you've used on those 2 sides. That's how they came up with this expression. Okay, so now as we go forward with this, let's see, what else are they asking you for? Find the length and the width of the plot that will maximize the area. As soon as you see this expression, you know that they're talking about values at the vertex. So we're going to need the maximum x value, and you know that when we find the maximum x value, that there's a formula for that. So in finding this value, it would be, let's see, I'll do it right here. X is equal to opposite of B. Remember, this is the same thing as the h value at the vertex, over 2a and so now we have to look for the b value and the a value. Where does that appear in the problem? Because all we have at this particular time is these sides that are labeled x, and we have and this is called the length, and this is called the width. Length and width. So where do we find the b and the a value? Well, they told us to maximize the area. So think about, how would you get the area when you're doing a rectangular shape? We've done that plenty of times in previous math courses. Area is just length times width. So if we wanted a function based on these parameters here, we would use this as the length and this as the width. And then we're going to be able to see the a and the b value so that we can continue with what we needed to do to find the answer for part A. So again, the length is 450 minus 2x multiplied by the width. Then you're going to distribute to remove these parentheses. The x gets multiplied by the 450 as well as the 2x, the negative 2x. Okay, you may want to rewrite it so that you're clearly understanding that the a value is always coefficient in front of the squared term, not that you have to rewrite it, and the 450 is the b value. So we have an a and b value, and we can continue with our work for part A. Okay, so opposite of the b value, which is 450, this is b, and this number out here is a, over negative 2 times the A value. Oops. Putting the negative in the wrong place. So the bottom of this formula is just supposed to be 2 times A. The A value is what's negative 2. Okay, so this is negative 450. You can pop that in your calculator, divided by negative 4. And then since you have a negative on the top and the bottom, it's going to be positive. Oops. So negative 450 divided by negative 4 is 112.5. All right, so we already know that this length right here is 112.5, and this is in meters. Okay, then as we continue with this problem, in the next question, part B, if we already know the x value, that x value will help determine what the length is. So we're going to go 450 minus 2 times whatever we found for x, which was 112.5. So this is 450 minus 2 times this is 225, but you can put it in your calculator, and you'll get 225 meters. Okay, moving on to part C. Okay, for part C, what is the maximum area? Well, the maximum area would be the area that you get when you use the length and the width that we have found, because what we have just found are the two, is based off the maximum x at the vertex. So when we're going to go maximize the area, remembering again that area is length times width, but if we use the numbers that are going to maximize the area, we would have the 225 for the length, so we got in part B, multiplied by that x value that we got, which was 112.5 meters. Okay, then you can toss that in your calculator, and it's 225 times 112.5. So we have 25,302.5 meters squared. Meters times meters, meters squared. Okay, that concludes section 3.1. We did everything from standard form equations to general form equations, concentrating on it opens up based on the A value, the vertex, how to find the X-intercepts algebraically, specifically concentrating on solving techniques such as square root method, factoring, and also finally the quadratic formula that we used in the application problems. We also learned how to put all of that information together, including the Y-intercept, onto a graph, which we then looked at the graph and were able to develop the equation for the axis of symmetry, as well as stating the domain and the range, and then we took those concepts and used them in application problems. So that concludes everything for section 3.1.